In chapter 3, we're going to spend a lot of time talking about the derivative. So what you've been doing in your algebra classes prior to calculus is learning about the slope of a secant line, which is between 2 points. And that's the slope formula, also known as the average rate of change and also average velocity. In late chapter 2, you were introduced to this formula, which is the instantaneous velocity formula. It's essentially the slope formula. It's the same thing as what you've been doing here. It's just that we're dealing with 1 point instead of 2. So the derivative is the slope of a tangent line. It's not between 2 points. It's technically between 2 points, but the points are so close together. Like this is still the difference of the y coordinates, and this is still the difference of the x coordinates. However, the difference between the x coordinates it's so small, it's 0. The limit as h approaches 0 means that there's 2 points here, but they're literally on top of each other in terms of x. Like the x coordinates are like really so close together that it's essentially 1 point. Here's another alternative formula for the derivative. And you worked on these in late chapter 2. This chapter will go into more formulas and less tedious ways of finding the instantaneous rate of change. But the derivative, the definition of a derivative is the slope of a tangent line, which is instantaneous rate of change, or velocity, also known as velocity. So say you're given this table and you're asked to find the estimate value of the derivative at x equals 6. So notice you're not given a function of x. So you can't use that formula. You can't do anything. You just have points. You can't make any assumptions about f of x except for these points that you know. So because you don't have the actual graph or any other information about this, the only thing you can do is estimate using the secant line. Can't take a derivative when you're not given the function because you can't find the instantaneous rate of change. Just because there's a point at 6, -3 doesn't mean anything. Like if you plot all these points, the two closest points are 2 and 7 on the x-axis. And 7 is, fairly close, but this one's not close really. So here's the strategy. If you're not given a function to take a derivative of, you can estimate using secant lines. So what you do is you find the slope of the secant line of between 6 and 7. So that's just the average rate of change formula, the slope formula that you've been using. So that would be the difference of the y's, -6 minus -3, and the difference of the x's, which would be 7 minus 6. This is the y2 minus y1 and x2 minus x1 equation. And then you find the difference, or you find the slope of the tangent line, the slope of the secant line between 6 and 2. So you take the slope of the secant line of the two closest points. So in this case, the difference in the y is -3 minus 5, and then 6 minus 2. You end up with -8 over 4. So now you have these two estimates of the slope of a line closest to 6. And now you can find the average of those two. So average means add them up and divide by how many there are. So in this case, -2 and -3 makes -5, and then divide by 2. So it's -5/2. That would be a close estimate of what we could expect the tangent line to look like. It's rough, but it's the best we can do when you're just given points. So find the slope of a secant line of the point to the right and the point to the left, the two closest points, and then take the average of that. Okay, our next example, we're actually given the equation. If f of x is this equation here, it's a times the absolute value of 3x minus 6 plus a times x. A is a constant. Find the derivative at x equals 2. So a is some unknown. You're going to learn a lot of formulas in this chapter, lots of derivative formulas. But you just have to remember that in order to be differentiable, a graph has to be smooth and curvy and pretty. And in this case, this graph is not. Now, we don't know what a is, so I just pretended that a was 1, and I graphed this equation. If you make a equal to 2 and 3 and 4, if you make it larger, it makes this more narrow. And if you make it a fraction, it makes it wider. If it's negative, it's upside down. If you remember that from absolute value, this is technically a stretch. And this doesn't play too much of a factor. This is very dominant in terms of what happens to this graph. So if you can just play around with it. That's what I did, and I just went with 1 just to graph it to give you guys an example to look at. The thing is, this graph is not smooth and curvy where we're being asked to find the derivative, which is at x equals 2. And you can figure out where this happens. This is the vertex of the graph, by setting the inside of the absolute value equal to 0. This gives you the x-coordinate of the vertex. So in this case, the x-coordinate of the vertex happens at 2, which is where the sharp corner is going to be. So f of x is not differentiable at x equals 2. So this does not exist. However, if we were asked to find the derivative of really any other point but x equals 2, we'd be able to find it because it would just be the slope of the tangent line. And honestly, in this case, this is a line, this is a line. It would just be the slope of this line. So the derivative is actually the same for every x coordinate because the slope is the same all the way down here, and then the slope is the same all the way up here. So you would just have to find the slope of the line at the point they're giving you. And in this case, because the graph is a line, that's a pretty easy problem. You don't have to estimate it. But because of that sharp corner at x equals 2, the derivative does not exist here. Okay, next one. This one's asking us to identify which graph is the original and which is the derivative. So there's a couple of things to do here. Best way to start is to look for horizontal tangent lines and then corresponding x-intercepts. Horizontal tangent line, remember the derivative is the slope of a tangent line. So if you have a horizontal tangent line, that means you have a horizontal slope. You have a line that's horizontal. The slope is 0, which means the derivative will be 0. So if you have a graph that has a horizontal tangent line, that means its derivative will equal 0 there. So the value of the derivative will equal 0 at the same x value where the original graph will have a horizontal tangent. And now this happens at a maximum and a minimum. Maximum, minimum, let me say that right. A relative means roller coaster. You're going to learn like the word absolute maximum and minimum later. And that just means like the absolute highest or absolute lowest, which is not necessarily a hill or a valley. Like I always remembered relative and roller coaster, meaning that it's like a nice hill or a valley. So this is a hill, this is a valley, maximum, minimum. This is also a minimum. So if you look at the two graphs, notice there's horizontal tangents of the red graph here and here, meaning if we were going to do tangent lines, like tangent lines of this red graph would look like this. Like this tangent line is positive. It's steeper here, steep slope here. So the derivative is a higher number here. It's starting to flatten out a little bit here. Starting to flatten out here. So like each of these lines that I'm drawing represent the slope of a tangent line. So if you were going to plot points on the derivative, this number would be higher. Then it gets smaller and smaller and smaller because the rate of change is smaller. The steeper the line, the higher the slope. And when it's flat, it equals 0. The slope of a horizontal line is 0. So at this maximum, the derivative will equal 0. Notice that there's an x-intercept right there. That means this blue graph equals 0 right there. And the blue graph equals 0 right here as well, which is at the same place that this horizontal line happens. So that's best way to indicate, at least narrow down your options when you're given a graph situation, is try to find maximums and minimums, hills and valleys, and then corresponding x-intercepts. Because if a graph has a horizontal tangent line at a point, then the derivative will equal 0 at that point. So right away we can narrow it down because this minimum here does not have an x-intercept to go with it. So the blue graph is the derivative, the red graph is the original. The blue graph equals 0, the derivative equals 0, where there's a horizontal tangent line on the original. Next one. So again, same kind of idea. Let's look at it a different way. Like we can use that same theory that I just showed you and narrow this down right away because this is a nice horizontal tangent and look, there's an intercept to go with it. But let's say that there's more than two graphs. Like you're going to get some that have the first, second, and third derivative or the original and two other graphs. So you need to like identify. Sometimes it's not as easy. So you can also look for where a graph increases and decreases because think about it. This blue graph is decreasing all here. So all of these tangent lines are negative, which means its derivative will be negative. And over here, all these tangent lines are positive, which means its derivative is going to be positive. So the slope of a tangent line is positive when a graph increases. So the derivative will be positive on the same domain that the graph of the original is increasing. So just check this out. So we have this horizontal tangent line right here, which means that's where our derivative graph will equal 0. Everything to the right of this x-coordinate, the original graph, I'm just going to label this f of x now because we're pretty sure that's going to be the answer. So that graph is increasing, which means that graph has positive tangent lines. So that means its derivative everywhere on this side of the x-axis, the derivative should have positive coordinates, which it does. Notice it's all positive here. And the same concept goes for where it's decreasing. Down here is where it's negative. All of these negative tangent lines, again, it equals 0 right there. So it equals 0 here. Everywhere to the left of this point on the blue graph is decreasing. It has negative tangent lines, which means its derivative better be negative for every point to the left of this x-intercept. So that's another way of narrowing it down. So you kind of start out with the horizontal tangents and find the x-intercepts, and then if you can't narrow it down more from there, start looking at where the graph is increasing and decreasing and matching up the derivative graph based on if a graph is decreasing, its derivative will be negative. Negative is below the x-axis. If a graph is increasing, its derivative will be positive, which is above the x-axis. Okay, so this one, the blue graph was f of x and the red graph was the derivative. One more. Okay, so this one, I'm not sure about this one. We've got a horizontal tangent line there and there. There's no x-intercept to match it. And this one, there's no horizontal tangent, so we can't really tell what's going on here. There's really not enough information on this one to make any conclusive decisions. So can't really do much with that. I mean, this is negative here, which would mean that the red graph would have to be decreasing, but it's increasing over here, so that doesn't make sense. And it has an x-intercept here, so that means if this was the derivative graph, there would be a minimum or a maximum on the red graph right there, and there's not. So nothing we can do with this one. It's just not enough information.